Okay, so welcome to Astronomy 101. I'm really glad you're all here. This is going to be a lot of fun, and I just want to say, if you're here on Twitch, be sure to hit the follow button and think about subscribing so you can help me meet my goals this month. If you're watching on YouTube after the fact, then feel free to hit the like button and subscribe for notifications on when new videos are posted. It really helps me keep bringing this to you, and all the links that I mention are down below. So, again, thank you all for being here. We are going to teach Astronomy 101 now. Hey, Josh. The reason for doing this is a lot of people have just asked, I want to learn astronomy. We were doing this sort of astronomy club where we were doing Q&As and what's in the sky this week, and it was great, but I think a lot of people were just kind of wanting some Astronomy 101 content. So how we're going to do it is I'm going to do each week, we're going to do a half-hour class. I'm going to run through the same sort of semester curriculum that I used to do when I taught Astronomy 101. And then we'll aim for like half an hour there, and then we're going to aim for like a half-hour type Q&A as long as we got. So, hey, Brad and Becca, everyone's here, and Josh. I'm really happy to have you all here. So this is going to be fun. And if you're here but not chatting and just want to sit and listen, that's okay too. So again, I put together a PowerPoint, and I'm trying to make this as license-free as possible. So I'm using curriculum from a textbook that I have used. If you do want the name of the textbook, then feel free to DM me, and I will get you details. But if you wanted to follow along with that, but because this isn't offered as a actual lecture course, and funds aren't, it's just laws and licensing and whatever, and I don't want to get my stuff taken down. I want to make these free classes, and so the images, there's not going to be as many images as I would hope, but if I'll try to find as many sort of free images as we can as we go through this. But to kick things off, first we're going to do what's up in the sky this week. So the moon is in its waning crescent phase, which will mean more to you once we get to phases of the moon during this class. And which means it's basically going from being a half moon to being a what we call a new moon. And so it's waning. That means it's getting smaller. And it's in its crescent phase. So we'll get some really cool crescent images in the moon. Hey, Mikhail. Thanks for being here. So the other thing is Jupiter and Saturn will rise in the night sky locally a little bit after midnight, and then Venus and Mercury should be pretty close to each other during the sky this week, about 30 minutes after sunset. So that if you want to sort of start trying to find planets and the moon and all that fun stuff as we learn, that's what's going on there. So let's kick off and start doing astronomy. Exploding eye, exactly. I am just screen sharing one of my monitors. I played with a bunch of different configurations, and this was like the least complicated one of all of them. It was an adventure. So let me sort of get everything set up so I can still see the chat, so we can still do all of this. All right, excellent. So what we're going to be talking about this week is essentially our place in the universe. When we start Astronomy 101, the hardest thing to wrap our minds around is how big space is and how insignificant we are. So the first thing that we do in any day one of Astronomy 101 class is we break brains. So sit back, enjoy, and again, I'm trying to make everything as license-free as possible. But if you've seen, there's great quotes from Hitchhiker's Guide to the Galaxy, and then my favorite is the opening from Futurama, where Fry just says, space is big, so big, until a gorilla comes out and starts shooting things at you. But anyway, there is a lot of it. So I am going to not have that much math in Astronomy 101. When I taught it, a lot of people take Astronomy 101 because they need to get a science credit. Space is objectively cool. And they figure you just get to look up at the sky at night. And, oh, thank you. And, But the little math that we're going to have is we are going to be throwing around big numbers. So I just want to go over scientific notation again really fast in case you don't remember how this works, because the few numbers that we are going to be throwing out, we will have to use scientific notation because space is really big. So if we say 3 times 10 to the 8, that means a 3 with 8 zeros after it. Now, we are hardly going to be dealing with decimal points at all because we're in space. Space is very big. Decimal points are for things that are very small. And our orders of magnitude are factors of 10. If we have, for example, 4.1 times 10 to the 11th, then you write down 4.1, and then you move that decimal point 11 times over. So that'll be 4, 1, and then 10 zeros because we already moved it 1 to account for the 1. I'm so sorry. I promise this is like as much math as we're ever going to deal with in here. Oh wait, we are going to do Kepler orbits. There will be some math in there, but I'm here for you. This is why we're going to do this, and it's going to be fun and it's going to be easy. So this is more the type of orders of magnitudes that we're going to deal with. 10 to the 42 is not even like possible. Because if any of you remember the Powers of 10 video, does anyone remember the Powers of 10 video that you watched in school that has been around, I feel like, as long as we've had VCRs in classrooms? But this is the one where it's like you zoom in each power of 10 and it gets smaller, and then you zoom out each power of 10. And we're actually, that's going to kind of make sense. It is hard to wrap our mind around. It has to do with exponents. But when we start to look at the actual distances between things, even just adding a couple zeros, you're talking huge scales. And just try to remember that Power of 10 video. And thanks, Becca. I'm glad. So space is really big. We are going to have to use scientific notation. And the units that we're going to use, because kilometers start to lose a lot of their meaning, as you'll see shortly. But if we want to look at things like within our own solar system, we'll use astronomical units, and then we'll also use, for dealing with like between star systems and galaxies, we'll be using light years and parsecs. We're just going to focus on light years today. Parsecs can get very complicated very fast. Even though all of us know the Star Wars retcon of the Kessel Run. So most of us know that parsecs are a unit of distance, but how you actually get to that ruler and what that unit of distance is hard to wrap your brain around. If you just can't wait to go figure that out, I do have a Dr. Aaron YouTube video on parsecs that you can go watch now, or just stick with me every week and we will eventually get to it. Now, like I said, we're going to go into each of these. Now, I skipped ahead a little bit. The 10 to the 42, like I said, 10 to the 42 is not really possible because that's so many zeros. But the thing I wanted to point out on that bullet is there will be times where we literally just use 10 to the something. We don't even put a 3 times in front of it. We're really just using 10 to the 13 or 10 to the 20. And that's what we call kind of order of magnitude, that our understanding of the level of detail, we can't even distinguish between 3 or 4 at that point, like 3 million or 4 million. We just know it's the order of millions. So we would just say 10 to the 6 because it's on the order of millions. We couldn't even tell you what number is in front of that. So that's going to be important as we start looking at where we live and what our place is in space. So again, if you've followed me for a long time, the cosmological address is something I drive home a lot. When people ask me what is the most common thing that I have to correct at for like science fiction writers when I'm doing consulting, is the cosmological address. And what that is understanding, again, scales, where we fit in our universe and what these are. So let's look at our personal cosmological address. What we mean by that is if we're writing to a letter to someone here on Earth, it'll look like this. It's on brand. You'll put where you live, what street, what city, what state, and then the country. Sometimes, if you're writing to people in other countries, then you'll want to include that. If you're writing in your own country, you won't necessarily need that. And then some places have things like postcodes or zip codes to help narrow down, because jumping from street to city sometimes scales too quickly. But that's sort of your address. So you start small. You say, okay, I live at Starfleet, which is on Lincoln Boulevard, which is in San Francisco, which is in California, which is in the United States. And you don't really feel the need to say Earth, because that's sort of implied there. But if we were writing to another alien, we would add Earth. And I'm going to include the distances on here just, again, so we can kind of start to wrap our head around. Remember, part of day one of Astronomy 101 is breaking your brain and feeling incredibly small. So we write our letter. We say we live at Starfleet on Lincoln Boulevard in San Francisco. I made up Lincoln Boulevard, by the way, because it kind of looks like where it should be. In San Francisco, in California, in the United States, on Earth. Earth is one of the planets in our solar system. We will learn all of these over the next few weeks. The solar system is one star system in our Milky Way galaxy. Our Milky Way galaxy is one galaxy in what we call our local group. So we have sort of a grouping of galaxies that are gravitationally bound to each other. We then have a local supercluster of galaxies. So if you're zooming way out, the way our universe looks, and I will show pictures of this once we get to that stage in this course, it does almost start to look like neurons or a mycelial network. I've talked about it in some other things, but it does just look like this weird webbing, and that's driven by gravity. But you can get these clusters, what those webs look like. Those are what we would call local superclusters, and ours is part of that. And then the universe. The universe is everything. So again, if you're writing your address, you live on a planet, in a star system, in a galaxy. That galaxy is part of a group of galaxies. That group of galaxies is part of a bigger cluster of galaxies, and then you all live in the universe. So places where we see this messed up is sometimes people will say, oh, those aliens came from another galaxy. Well, did they? Because galaxies are very big and very far away from each other, and there are hundreds of billions of stars in our own galaxy. Chances are they're coming from that. Again, it's all distant scales. I put the sort of relative size scales here. Remember, we talked about AUs, which are astronomical units, and I'll get into those next, how we define those. And then when we get to sort of star systems and galaxies, that's when we start talking about distance units of light years, because that's then a little easier to sort of write down and wrap our heads around. Because when we say something, I put the kilometers in there. Again, power of 10. Remember, it's exponential, the power of 10 video. We're going from the Milky Way galaxy, which is 10 to the 18 kilometers, up to our local group, which is now 10 to the 19 kilometers, to our supercluster, which is 10 to the 21. That's a 1 with 21 zeros after it. How can you even wrap your head around that? You can't. We just can't. So translating it to light years helps us scale it a little bit better. It helps our brain understand these relative distances much, much easier. So going from something like 100,000 light years being the size of our Milky Way to 3 million light years, we understand intuitively scaling 100,000 to 3 million. We can sort of picture what that difference means. And then scaling the 3 million to 100 million. We can picture that a lot better, as opposed to just saying, oh, it's from 10 to the 19 kilometers to 10 to the 21. At that point, our brain is like, yeah, it's big. I get it. It's just big. And the last thing I want to drive home with this cosmological address is the fact that our universe is everything. So when certain beloved, deeply loved, favorite shows throw around a local star system as the verse, which is implied to be short for the universe, is a little misleading. They don't mean the universe. They mean their star system, which is nicknamed the verse. Just to make that clear. All right. So now that we're good with that, going into those astronomical distances that you may have not... Oh, Billy. The Voltron thing. Hold on to that. Remind me during the Q&A and I will vent about the Voltron thing. I'm still mad. I may get upset. And I have to make it through this before I start to get upset. And then in Mass Effect uses local cluster a lot. Are they using it wrong? That's a really good question. I'll come back to that one as well. So we can sort of get some clarification. We can clarify that a little bit better. But yeah, feel free to throw questions in the chat. We will do questions too when I'm done. We have plenty of time for questions after this. So yeah, whether you post them now, whether you post them after, we'll do them. We'll do them once we're done. But I've threw out Astronomical Unit, AU, and I threw out light year. Light years you might have been familiar with. Astronomical units you may not be familiar with. Those are really units that we just use to deal with in our solar system. Because, again, similarly, if you're saying a planet is 380 million kilometers and that planet is 150 million kilometers, we know that that's sort of, we can kind of picture that, but it's hard to wrap our brains around that as well. So we've made up a ruler to use for our solar system called an AU. And it stands for astronomical unit, and all it is just saying, let's take the Earth to the sun and just call that our ruler. That's one AU. And so then you have planets that will be less than AU. Those would be Mercury and Venus. And then bigger than an AU, you would get out to Mars and Saturn and Venus and all of those. So that helps us understand scales a little bit better, because when we jump from maybe 0.2 to 0.5 to 1 to 2 to 30 to 60, we can picture that a lot better than just piling on millions of kilometers. Now, light years, again, you're probably familiar with, but it's hard to sometimes wrap our head around. So I just want to take a second and let's talk about what a light year actually is. I'm sure you might have in the recesses of your brain somewhere this idea that a light year isn't a unit of time, even though it has the word year in it. It's actually a distance. So we say something is light years away. We mean that that's a distance, not time, even though sometimes we use that interchangeably. But what it's defined as, that ruler, whereas the AU is the sun to the Earth, that ruler is the distance that light travels in 1 year. So if I shine a light here, that photon travels, and it travels, and it travels, and it travels for 1 year. However long it takes to get there, in 1 year, how far it's traveled is a light year. It works out to be about 10 trillion kilometers, 10 to the 12 kilometers, which is hard to wrap our brains around as well. And we really use a light year to describe distances of stars and galaxies. And again, it's a unit of distance, not time. So I'm going to sort of expand. We're going to start small. We're going to get big to help wrap our brains around this. Again, this lecture is meant to break us a little bit as we head out into the cosmos. Light travels at 3 × 10⁸ meters per second. If you took physics but not astronomy, you're familiar with that number because it's a good standard unit that we use. What that really is saying that in 1 second, light has traveled 300,000 kilometers. And that's about 8 times around the Earth. So light goes very, very fast. If we leave the Earth now and going out into the cosmos, the sun is 8 light minutes away from Earth. So when we don't look directly at the sun, but through a solar telescope, for example, you're seeing the light as it left the sun 8 minutes ago, because it's taken time to reach us. And it takes 8 minutes. So if something weird happens on the sun, it takes 8 minutes to reach us, and we will not see it any faster than 8 minutes. Which is a little disconcerting, but also that's not too much time. So that's okay for us to kind of understand. But we're seeing the sun as it was 8 minutes ago. Sirius, which is one of the brightest stars in the night sky, it's not the closest one to us, but it's one of the brightest ones. And it's also the name of a beloved Harry Potter character, so we use it whenever we can, is 8 light years from Earth. Again, very bright in the night sky. You can see it with your naked eye very easily. And it's 8 light years from Earth. When we see that light has been traveling for 8 years. It was emitted from the star 8 years ago and has traveled through space to us. So we're seeing that star as it was 8 years ago. Keep pulling out from there. The Orion Nebula, so the Orion constellation, also fairly easy to see in the night sky. We have Orion's belt. If you zoom in on that, there is a nebula there. You can not see it with your naked eye, but you can image it with a pretty, on the pretty basic telescope, which is awesome. It's a star-forming nebula. Don't worry about what any of those are right now. We will get to all of those in upcoming classes. I love teaching classes again. But it's 1,500 light years from Earth. So this is a star-forming region. That means that it's very dynamic. There's a lot going on here. Again, don't necessarily worry about what that means. The main thing to take away here is this image that we're seeing is as that nebula looked 1,500 years ago. It sent out all this light, and we are getting it 1,500 years later. Now, the nice thing is that space is very, very, very big, and so 1,500 years is not that much when you're talking about the life cycle of a star, which is on the order of billions of years. 1,500 years, we can kind of say that probably hasn't changed that much in the interim time. Unless you have things happening like supernovas, those transient events that just happen and then they're done. Obviously, if one happens now at the Orion Nebula, we won't see it for 1,500 years. But a cool way to sort of translate that to where we are here on Earth, this is like we were seeing this as if this is what was going on the Orion Nebula when the Roman Empire was going on here on Earth. So that was happening simultaneously. It's just taken time for that to reach us here. Is the Orion Nebula the closest nebula to our solar system? That's a really good question. I don't think so. It may be the largest, like the biggest closest one, the one that we can get the most detail out of, but I will look that up when we're doing our Q&A, and we can figure that out, because I have no problem doing that. I do not have everything memorized, and I'm fine with that. But I will help look things up and translate the answers for everyone. Now we're really going to break our brains, because the Andromeda Galaxy, our closest major spiral galaxy, this is our local group, which now you sort of know is our little cluster of galaxies, has 2 big spiral galaxies in it. The Milky Way that we live in and the Andromeda Galaxy. And then some smaller globular galaxies, which, again, we'll learn about. But the Andromeda Galaxy is 2.5 million light years away. So it's very, very far away from us. And the cool thing with this, too, is we're not only just seeing it as it was 2.5 million light years ago, or 2.5 million years ago, but also the fact that because it's 100,000 light years in diameter, when we're seeing stars on the other side of that, that light has traveled for 100,000 years before it left the galaxy itself. So there's a lot of time travel that's just happening in that one picture, which is pretty cool to think about. So yeah, space is big and it takes time. And really, when we're observing stuff in space, we're looking back in time. We're seeing stuff as it was. And so we always have to put that in the context. So now thinking about our universe as a whole, the Hubble Telescope, the Hubble Deep Field Telescope, basically opens its aperture and just lets light hit it. So it lets the furthest away galaxies, we can observe them. And we've observed galaxies that are 12 billion light years away, which means it's taken 12 billion years for that light to reach us. Because of that, when that light happened, when that light was emitted, our universe was only 2 billion years old. So it was like a young little baby universe. And hey, Raj, thanks for joining. So our universe was only 2 billion years old when that light was emitted. So these are little baby galaxies. They're little babies. And when we talk about our observable universe, when we talk about the universe as a whole, the Big Bang happened, and I'll get into that next. It happened 14 billion years ago. So the furthest distance we can see is 14 billion light years, because light has only taken that long to reach us. So when we talk about the Big Bang and the expansion of our universe, and I'm sorry, exploding high, that's, I think, probably the face that everyone's making right now. Our universe is expanding. Things are moving away from us. I'll hit that note again and talk about that a little more detail in a second. But on our smaller scale, gravity draws the galaxy clusters together. So our universe is expanding, but you do have these clusters that are held together through gravity. So it's really just a size scale that dictates what's happening. I'll come back to that. But the stellar cycle, when we're talking about like within galaxies, so the Big Bang happened, the universe starts to expand. Everything gets further and further apart from each other. And that's a good question, State. We are 14 billion years from the Big Bang. So everything has moved apart from each other. And we can look and this is the hard part, and I'm glad you all are asking these questions, because these are the questions that need to be asked here. And Raj, quite similarly, how accurate can it be calculated? There's a few things that go into that. One is the fact that we can see how fast everything is expanding away from us. These are bullet points further back, but because we're asking, I'll go into it now. You can look at the further away ones and see that those ones are moving very fast away from us. You can backtrace all that data and see that we all kind of started at one point, and then it expands out. And as it expands out, it starts to cool, things accelerate, they move far away from each other, and that heat starts to go down. So, Raj, I'll answer your other question when we're done with sort of this part. We do like a Q&A at the end of this, because that's a really good question too. But we have something called the cosmic microwave background, which is essentially all that latent heat that was left over from when the Big Bang happened. So that's kind of where that came from. But so the Big Bang happened, we just had all of this matter, and we will talk about cosmology. We'll talk about like where that's coming from and all of those details there, because there's a lot. It's astronomy. As it expands, though, we had all of these sort of gravity took over. Gravity collapses these just generic clouds that existed. They form stars. Those stars start to form these clusters of stars that we call galaxies. And then when the stars die, they return that fuel back out into space. So a lot of us have sort of that, beautiful philosophical statement that we are star stuff is absolutely true. This is basically just like a trailer for the rest of the semester. I say semester. I went back into professor mode really fast for all of the rest of the classes that we're going to do. So don't necessarily worry about like Big Bang fusion, what that means, cosmic rays, exploding massive stars, white dwarfs, low mass stars. We will get into what all of those are. The point is that understanding that we have this cycle of life that happens in space where stars form, they fuse elements together, then they die and return that back out. And that's been going on for 14 billion years, and that's what's filled everything that we see and observe through space. So let's talk about really quick the universe in perspective, because I haven't broken your brain enough. I thought I'd just lay in one more as we close out this first section here. Let's just break down the 14 billion years into a calendar. Big Bang happens at 12 midnight right at the beginning. Milky Way was born-ish early February. Then we go down... Exactly. The Milky Way, our own galaxy, this whole cluster of stars, doing its thing. Stars are forming and dying and forming and dying. And then our sun forms. And then out of Again, we'll learn all these details, but our star formed out of a cloud of dust and gas, and from that cloud, not just our sun, but all of our planets. So this is 4 billion years ago, 4.5 billion years ago, approximately, would be in September. Then early life, then dinosaurs, then the extinction event, the dinosaur extinction event, and then right in December, right at the end, we have where we are now. So again, this is all scales of time. And when we're talking about something like observing super young baby galaxies, those are the ones that maybe formed like mid-January. So they emitted that light back in January. We're only getting it now. And so it's really fun to think about. And this will all start to get easier the more we go through this. So I hope you keep coming back every week. This is all sort of a precursor just to get your mind a little bit thinking about the scales of distances and time that we're going to be referring to all throughout this Astronomy 101. This last thing that I like to end on here for our first class is this concept of spaceship Earth. That we live on Earth. I'm sitting here, I'm relatively chilling, and I don't feel like I'm moving that much, but Earth is moving through the universe all the time. And that's one thing to say, but it's another thing to actually understand and try to grasp. So the Earth is spinning. We're staying down on it because gravity's cool. but that rotation is on average 1,000 kilometers an hour. The Earth is orbiting the sun at 100,000 kilometers an hour, so we're rotating. Earth is going around the sun. The stars that are nearby are kind of randomly moving around at about 70,000 kilometers per hour. Our whole randomness of our solar neighborhood is going around the galaxy at 800,000 kilometers an hour. The Milky Way and Andromeda are heading towards each other at 300,000 kilometers an hour. And then once you get outside our local group, all the galaxies are moving away from us. And like I said earlier, the more distant, the faster it's moving away. So to close this out, and you can start typing your questions now, we have our cosmological address. If you missed it at the beginning, we talked about the fact that we live on the planet Earth, which is a planet in our solar system, which is one star system in the Milky Way galaxy, which is one galaxy in our local cluster of galaxies, our local group, and then we have our local supercluster, and then we have our whole universe. Space is big. We're going to need to use new units to measure distances, so we talked about astronomical units that we use to measure solar systems, star system scales. Basically how far planets are away from stars. We use astronomical units, and then we use light years to talk about the sizes of how far apart stars are from each other and how far apart galaxies are from each other. When we observe space, we're looking back in time because light takes time to reach us. Even though in 1 second a light particle will travel 8 times around the Earth, space is big. And it takes years for light to travel from stars to stars. So when we observe things in space, we're looking back in time. We are made of star stuff. We will get all into what solar cycles are, what nebulas are, how stars die, which is fabulous and amazing. And all of those elements, everything we see and touch, just comes from that cycle, that life cycle of stars. Here on Spaceship Earth, right now, right as you are sitting listening to me, whether you're watching it live or after the fact, we are booking it. we are flying through the cosmos. About every second we move a few hundred kilometers. So that's fun. And the universe is expanding. This was something that was observed by Hubble in the early 1930s. We will learn more about Hubble. We will learn more about universe expansion. And I did have a few questions, so we'll talk about that now as well. But those are sort of the big takeaways for day one. It's all about putting us in the context of space. understanding where we are in our universe and trying to start to understand how far apart things are and what these time scales are that we're going to be dealing with, because it's a lot. And as exploding high and a few other people mentioned, it's a little bit brain blowing. So I get it. I appreciate that. Let's go to some of the questions we had. I did have some questions, so you can carry on with that. But I'm glad you learned about AUs. So the first sort of question that we had was talking about the local cluster in Mass Effect. I don't remember them saying anything that was particularly wrong when it came to star systems and galaxies. If you remember the exact quote, we can try to look it up. I'm happy to do that, but I will try to poke around really quick right now as well. I'm replaying Mass Effect right now too, so that's for Mondays. All right, thank you. Because I think they were talking about, talking about that in another context, as opposed, so maybe like a star cluster or a different type of cluster. Oh, Voltron. Billy wanted me to mention Voltron again. So, if you do have questions, feel free to go into that. Thank you, parsecs. But Voltron broke my heart. The Voltron Legendary Defender series on Netflix is awesome. Don't get me wrong. I love it. Their use of wormholes and space-time and time travel and everything to do with general relativity and space-time, which is hard topics, was perfect. They threw out gravitational waves. They threw out gravitational instabilities, Lagrange points, crazy good stuff. And then they confused star system and galaxy. They were like trying to get back to Earth, which is our solar system. Then they said, we've made it home. We're home. We've made it. It's our solar system, the Milky Way, and showed a picture of a galaxy on the screen. And I just cried. So it was brutal. Yeah, it was very sad. All right. And then Raj asked about how accurate the age of the universe can be calculated. Like I said, I kind of alluded to it. There are lots of different ways that we can sort of trace back and look at it. But because we are able to have telescopes and observe in different parts of the electromagnetic spectrum, we can observe the universe back to its earliest days. So there's a point called recombination. We will learn all about this. There's a point called recombination, which resulted in the cosmic microwave background, and that's essentially how we date the universe. But again, if we're talking about on scale, order of magnitudes and everything, we're talking about 14 point-ish billion years. That's our accuracy scale of how good we can do. So if you want like a plus or minus, we're on the order of maybe tenths of billions of years, if that makes sense. And then the cosmic web. So if you had a question about my thoughts on the cosmic web, are you just talking about the overall superstructure of the universe that kind of looks like a web? That was a simulation, and we've also seen it just through observation, that shows that galaxies do form this sort of, let me see if I can pull up a picture of it really fast. Yeah, that's a great picture of it. All right, so let me just pull this over here. Yeah, you can see that. That's from a simulation called the Cosmic Web. And that's the output of a simulation that here, I'll leave it up for a second. But you essentially took like a uniformly distributed particles, and you just let gravity take over. So you say, okay, they're uniformly distributed. They're going to have some error on how exactly uniform they are. And then you just say, okay, gravity go. And it eventually, over billions of years, forms something that looks like this, which does match what we see observationally. When I did radio astronomy, I was observing sort of our local universe, and which you're on the scale of galaxies. And as you go through, different spectrum, and you're going back in time, again, back in time, further in space, it was like forming a chain of galaxies. Like, you could see this chain that was forming, that's from this sort of superstructure of our universe. And I like it because this is my allegory for the mycelial network. So it works too. Okay, so questions about parsecs. It does equal about 3 light years, Raj. Thank you. We are going to specifically talk about parsecs. It will take like an entire episode to talk about it. Just simply because the way to calculate a parsec is a little bit difficult. I do already have a video up on my YouTube channel. If you look for Dr. Aaron Explains the Universe, there's a Kessel Run in Parsecs video where I break it down. So you can go watch that now, or you can wait until we get to it in the class. But it's essentially like, it's just a more complicated ruler. It's a more complicated ruler. It's how far away things are in, if we take our space all around us and you say, okay, this is 360 degrees. You break up each degree into 60 arc minutes per degree, and then 60 arc seconds per arc minute. And then how far away it takes for something to be one of those units apart. It takes it takes better graphics than me wildly gesturing at my camera. Okay. So let me see. So Exploding High had a great question about dividing up quadrants. So in Star Trek, they divide up our galaxy into quadrants. We have the alpha quadrant, the beta quadrant, the delta quadrant, and the gamma quadrant. How feasible is that, since we're discussing units of measurements, or is it better in real life to just label everything by their cosmic address? So that's a really good question. The quadrant designation in Star Trek is purely Star Trek. This idea that we live in the alpha quadrant and something's coming from the gamma quadrant, that's pure Star Trek. We don't necessarily do that as astronomers, but there's a reason for that. So I'll talk about our own galaxy first, then I'll talk about other galaxies. But if you talk about our own galaxy, the Milky Way, we see the Milky Way at night as this streak in the sky. And so I've talked about the term Milky Way galaxy being the galaxy that we live in. And some of you might be wondering, wait, but I see the Milky Way in the night sky. So what is that if the Milky Way galaxy is what we live in? Valid question. They are the same thing. And it just has to do with the fact that our Milky Way is a spiral galaxy and we live inside that spiral. And so when we look down the plane of our galaxy, we just see it as a line. So if you look right down this plane, you just see it as a single line because you live within that. But because of that, it makes it really hard to map the other side of the galaxy, because you see those bright spots and you see those dark spots. Those dark spots in the Milky Way aren't an absence of something. They are actually dust that's keeping us from being able to see stuff on the other side. So it's really hard to map out our own galaxy. Any pictures you see of our own galaxy are artist renditions of comparing us to other spiral galaxies that we see. When it comes to like looking at other galaxies and being able to map those out and using distance of measurements and figuring out where things are and using sort of a quadrant system, I'm so sorry to lay this on you, but if you remember in math, I know it was a lot of people's worst experience, was coordinate transformations from linear coordinates, x, y, and z, to cylindrical coordinates, if you remember those, where you have the distance from the radius and your degrees around and then your z. That's probably the best way to actually map out star systems from the center of a galaxy, to say how far away from the center it is, whatever reference point you're using being sort of the north, and then how high or low it is. And breaking things up into sectors is probably more accurate, but we've never really much had reason to do that. So, okay, good. I'm glad that made sense. All right. Oh, the James Webb Telescope is fully stowed. They put in a great Schitt's Creek reference when in the James Webb Telescope they said fold it in. If you don't watch Schitt's Creek, that means nothing, but that was really funny for me. So once it is set into orbit, what are we hoping to see? That is an awesome telescope question. So it's essentially supposed to be the it's supposed to be the next Hubble, essentially. And I'm trying to look up exactly which spectrum it's supposed to observe in, because, okay, so it has a few instruments on it, but it's actually primarily going to be more infrared. So there is, if you look up, I can't post links in the chat. I might be able to. Let me try. Since I'm the owner. Yes. I hope you got that. That compares the two of them. It will be more in the infrared than in the visible compared to Hubble, but it is still supposed to be a very deep field imager. And it has much more improved technology. So it's not just like the next Hubble, it's Hubble Plus. And has much more images. And it's actually like 10-minute drive from where I'm at, because it's in, I think, because it's all stored here, the Northrop Grumman out here. I've seen it. I've seen the James Webb Telescope. It's pretty cool. So, all right, then Domestic had a question on if the observed galaxy we're viewing is a distance of 12 billion light years, and this is how far away it was 12 billion years ago. Oh, that's a good question. So let me read out that question specifically. I kind of processed that as I was reading it. But if the observed galaxy we're viewing, so one of the galaxies I pulled up, if we say it is at a distance of 12 billion light years, and that's how far away it was 12 billion years ago, how far away is that galaxy right now? That's a really good question. And the answer is it's 12 billion light years away. It's not that it was 12. Let me think of how to phrase this. It's a really, really good question. So I want to make sure I answer this properly. It's not that. Let me see. Yeah, I understand the confusion. That's essentially like it's emitted the light, but the galaxy has continued to travel away from us. But that light is continuously being observed by us. So it's something called Doppler shift. And so it's 12 billion light years away from us, and we know it's 12 billion light years away because that light has taken that time to reach us, and it's Doppler shifted at a certain frequency. So we have to use that reference point of us being here, like us observing all that light and saying, okay, something is 12 billion light years away from us. That is what we're observing now. But our universe is continuing to expand, and it's continuing to age, and everything is moving apart from us. But again, it's those time scales, right? That's hard to wrap our brain around. So it's a really good question. I know I didn't do that great of a way to answer it. It's a chapter 5 question. I know I didn't do a great job answering that. We will talk about Doppler shift, and we will get more into those distances in those galaxies. I hate to not give you a better answer than that, but I haven't spent the enough time I need to answer that properly. So did that do enough to draw you in and hopefully not annoy you? You'll come back, I hope. Raj asked a question about my Star Trek video about wormholes and Einstein-Rosen bridges. How come we didn't mention quantum slipstream drive? quantum slipstream drive is another word for a wormhole, as is a incursion, as is all these other things. So you're right, we didn't mention quantum slipstream drive. That wasn't necessarily intentional. It was just a matter of they never really went into the details of that much, and it is effectively, so the way I view quantum slipstream, this is a bit of a tangent, but the way I've vision quantum slipstream drive is more like you're building your wormhole as you're traveling through that. I think, if that makes sense. Okay, and thank you, Domestic. I promise I will spend some time trying to think of a more concise answer for that. So, question from State. Also, the galaxy or galaxies speeding up. My guess is our location from the Big Bang. So do we know where the Big Bang started from? Again, awesome question. And it is hard to try to wrap our head around. So Hubble, Edwin Hubble, the dude, not the telescope, the dude the telescope is named after, is the one that observed that everything was moving away from each other. What does that mean? Where is the center? If we are here and we look up and we see the galaxies outside of our local cluster are all moving away from us, and the ones further away are moving faster, does that mean that we're the center of the universe? Yes and no. The analogy that we use is something called the raisin bread analogy. Excuse me. And if you can imagine raisin bread, as it expands, as the raisin bread expands, so you make this dough, which I know is a lot of people are doing these days. You make this dough, you fill it with raisins, and then you let it rise. And it starts this big, and then as it starts to rise, it expands, and it gets bigger and bigger. All of those raisins are going to look at those other raisins and see them all moving away. So each raisin is going to think that they're the center of the universe because they're going to see all the raisins moving apart from each other. But it's just because everything is expanding away from each other. So our universe as a whole is expanding. And in some sense, yes, we were all at the same point at one point in time, and then it all just started to get away from each other. Now, the bigger question is, okay, but raisin bread has an edge, right? Raisin bread does have a center. Raisin bread is expanding into my bowl and into my kitchen. So what is our universe expanding into? And we don't really have a good answer for that. We just know that our universe is indeed expanding. But that idea of everything moving away from each other, that's sort of the best analogy we have for it. Let me see if there's anything sort of smarter I can say that I can steal from this. And it really just has to do that space itself is expanding from that too. So everything started at one point, and then everything started to expand away from each other, if that helps. I know that's a hard... So I can't say, here's another good way of putting it. I can't say there is where the Big Bang started. What I can say is there is where the Big Bang started. That's the edge of the raisin bread. So I think there's some good images with this. If we talk about the let me see if I can pull one up. Where we talk about like the cosmic horizon. Here, this is kind of a good one. So if we talk about it like this, then maybe this makes sense a little bit. That it's more that we're at the center and we see everything moving apart from each other, and the edge is where the Big Bang is. I think it is probably an okay way to talk about it too. So I hope that makes sense. All right. Are there any last questions? If people are in the middle of typing or you're frantically trying to get one out, it is kind of like we're in a bubble. If you're trying to get one out, just throw like a quick letter or emoji or the first half of your question in the chat so I know to wait, because we still have a couple more minutes. But I don't want to end prematurely if someone's trying to ask questions. If you do, after this, have slept on it, processed it, hopefully didn't break things too much, You can always ask me questions on Twitter. It's at Dr. Erin Mack. The links, all my social links are down below. And then I will post this recording. Shoot, yeah, I did hit record. Whew. That was a panic. I will post this recording on YouTube, so you can throw in questions in there as well. More than welcome to do so. I'll try to keep an eye on those and answer those for you. I know this was a lot at the beginning. I really appreciate everyone sticking in there. If it makes you feel any better, this is the feeling you have right now is the feeling everyone has after their first day of Astronomy 101. And it's the feeling I have every first day that I have to teach Astronomy 101 is it's just like, all of these questions you are asking are great. And I promise we will give better answers to those questions. I hope I answered some of those now. But as we start, as with any course, right? It's about building knowledge. It's about building our understanding. You're welcome, Homer. And starting to wrap our brain around our place in the universe, what the universe means, what all those objects are that we see, where they come from, all of those things. We're just slowly going to build knowledge on top of each other. So it is a little bit of a brain dump at first, but as you spend the week processing it and thinking about, like, when you look up at the night sky, light has taken time to reach you when you are not looking directly at the sun, but you can think about, the light that you're receiving from the sun, that took 8 minutes to get to you. All of those sort of consciousness things are going to help make this course a little bit easier. And thank you, Exploding High. I really appreciate that. That makes me feel really good. I love teaching astronomy. And like I said, I would love to just lecture through pictures and Star Trek references and all of those things. But I do want to make this free and license free and not get banned and taken down. So, I think we can close out here, but I hope it is helpful. And I appreciate all of you taking the time to hang out and ask your very intelligent questions. I appreciate that. We're becoming all scientists, so you're very welcome, Benny. Thanks for being here. You're here on Twitch, so please don't forget to hit follow so you can know when I'm going to be on here next. If you are an Amazon Prime member, you can subscribe to a channel for free each month. So consider mine if you want to do that. Have a look. I really appreciate it. Or you can just subscribe. That's an option too. It's $4.99 a month. And then you get the cool emojis that Brad just used. So, again, thank you for watching. If you are watching the recording after this on YouTube, don't forget to like and subscribe, which helps me to keep bringing this content towards your way. And if you'd like to be more involved in my Astrometrics Lab community, we have a Patreon, and you can help us decide what science fiction we're going to talk about on our Tuesday episode clubs, and just lots of fun stuff there. All the links are down below. Thank you for hanging out with me this afternoon. We will be back. I will be back on Sunday to do our casual Trek brunch, where we talk about Star Trek episodes with a friend of mine who's watching it for the first time. On Tuesday, I have my episode club, where we talk about science behind science fiction. We'll be doing 2 episodes from Dark Matter, talking about Blink Drive and that. And then I'll be back doing this. And you're very welcome. Thank you all so much. I hope you have a good rest of your day. Please take care of yourselves. Get up, stretch, drink some water. Thanks again. We'll talk to you soon. Live long and prosper. Bye.